the material that we did look at as a way of just building up on those things that we did learn. So I ask all of us to be patient enough and move with us like you have always done. You've been very good students as far as I'm concerned. One of the groups that I have enjoyed teaching, you've been one of the groups I've enjoyed teaching. So we move together. And when your representative communicates to you yet again to ask us that we should find another slot where we can that we can use to continue learning this particular topic, please cooperate with him. If you have challenges, let him know so that you choose a time when everyone can manage to attend these learning sessions. Because once we present information the way I'm presenting, as far as I'm concerned, I will record to say I taught everyone, because the information was shared with everyone, and it is your responsibility as a student to log in and make sure that you learn with us. If on a given day you've got a different program and you are not able to log in and learn with us, we are not going to know, because as far as we are concerned, everyone is aware and they're supposed to be part of this arrangement. So like I have said, it is your responsibility as a learner, a student, to make sure that you find time to learn with us these things. So spare time to do this. Any time that you feel we can meet, for me, I'm very flexible. I can adjust my work schedule and make sure that I attend to you guys. Okay, good. So we get started with our new topic, which is called acid-base equilibrium, which essentially is just acids and bases. So it is called acid-base equilibrium because we focus on certain concepts that may be very much similar to what we did focus on when we were looking at the previous topic, which was the chemical equilibrium topic. So we start. So I keep switching between the applications because I have to keep admitting our friends who are trying to join in. In this topic, there are a number of things that you are expected to know as a student who is doing CHE 1000 as a course. You should know the nature of acids and bases, concepts that most of you are familiar with, I'm aware, but there is a way of how we may prefer that you should know them. You should know something about strength of acids. You should know about something about the pH scale, how to calculate the pH of strong and weak acid solutions. You should also know something about the bases and what we refer to as polyprotic acids. You should be familiar with the acid-base properties of salts, the effect of structure on acid-base properties, acid-base properties of oxides, the Lewis acid-base model, one of the models that we use to define acids and bases. Then you should also be able to solve problems that are going to be presented to you in relation to acids and bases. Okay, something that we are going to make sure that we do carefully at the end of the day for you to be able to answer questions effectively, the way you are able to answer questions from chemical equilibrium. I'm very sure of that fact. Okay. So a little bit of some history. You recall that acids, we were told that acids would have certain properties associated with them, physical properties by which they are identified, and we know that acids have got a sour taste. And an example that you might give of a substance that contains acetic acid is vinegar. Vinegar contains acetic acid, and that's why vinegar has got that characteristic sour taste. Then for the lemons, they taste the way they do because they contain citric acid in them. For bases which are soluble would dissolve in water to form alkalis, which are referred to as alkaline solutions. And they have got a characteristic bitter taste. That's the property by which they are identified. And they are slippery actually when you touch them. There are a number of concepts that we use to define acids and bases. What is an acid? What is a base? So we use different concepts, different concepts to define acids and bases, concepts and theories actually. And one of the theories that we are going to emphasize on. So a question may be designed where we ask you to define an acid using a specific concept. In this case, if you're using the Lewis theory to define acids, you define an acid as a substance that can accept a pair of electrons to form a new bond. So as far as Lewis, which is the name of a scientist who coined this particular definition, was concerned, an acid is supposed to be defined as a substance which would accept a pair of electrons to form a new bond. So acids also, as far as this particular theory is concerned, may be referred to as electrophiles. Okay, acids may be referred to as electrophiles or centers that seek an additional electron pair. A center that would seek an additional electron pair. Okay, we know that electrons are negatively charged, so in other words, it's a negative center seeker as it were. Okay, so using the same theory, a base is defined as a substance that can donate a pair of electrons to form a new bond. So notice the emphasis on formation of a new bond. So a substance that can that can donate a pair of electrons to form a new bond. So this particular substance, as far as Lewis was concerned, is supposed to donate a pair of electrons so that a new bond can be formed. It is also referred to as a nucleophile. A nucleophile is a positive center seeker. So anything that is going to target something that is as at a positive center, which can be referred to as a nucleophile, may qualify to actually be called a base. Something that you're going to notice as you go on learning your chemistry. That is, if you're going to do any second year organic chemistry, you will deal with these reminders to say those are called nucleophiles or electrophiles because there was some theory that was used to actually classify them as they are classified as such. Okay, so in short, a Lewis acid is an electron acceptor. A Lewis base is an electron donor. It's an electron donor. So if the representative is here, by the way, encourage your friends to participate in these learning sessions. I have been teaching from 12 hours. I actually started talking around 12 hours. In the previous lecture group, I had quite a very good turnout where the participation was around 80, 78 in one group. In another one, there were about 80. So when it comes to giving a report on whether everyone was taught, as far as I'm concerned, I will base my report on the participation that I had from the previous groups. The first session had 78, the next session had about 80 something, 82. The last session had a slightly lower number, about 50 something. So the turnout was very good. And I encourage that I advise that you talk to your friends. If you are here, you talk to your friends to be serious with these sessions. Like I have always kept on preaching to you, your examiner is myself, who is going to decide where your examination questions might have to come from, and they would come from the things that I am talking about here. So if you decide not to be here, then surely it is not going to be our fault. It is going to be entirely your fault because it is a decision that you will have made. The announcement was made by the representative and everyone is aware. So when I see less than 60 participants, it calls for some worry of some sort. We are just about 50 something. So I was expecting us to be somewhere around 70. Maybe others may decide to join in later. But talk to everyone. Caution them, tell them these classes are compulsory. If there was a way, I was actually even going to be carrying out a rock course so that when it comes to giving a report, in case any one of us does not perform very well and questions are asked, I would refer to the list of those that were attending to say these were the people that were attending. Those whose names have failed, I don't remember seeing them in my sessions. That is the explanation that I will have to give. So let everyone join in. These sessions are not optional. They are compulsory. It's an arrangement that has been decided that it should be used by the university itself, to which we all belong, you as students and me who is supposed to teach you. So moving on, another way of how acids and bases can be defined is based on a different concept, which is the Arrhenius concept. You have started looking at a new topic, which is electrochemistry, and in electrochemistry you will see this name will keep popping up, Svante Arrhenius, who did a lot of experiments electrochemically, that is. And while he was doing these experiments, he noticed a lot of a number of things that acids and bases were able to show in terms of their behavior when they were added to water, such that he was able to coin some definition of what an acid is supposed to be. So according to Arrhenius, an acid is any substance that is supposed to, when dissolved in solution, would result into an increase in the concentration of hydrogen ions. So any substance which, when dissolved in water, increases the concentration of hydrogen ions, qualified to be called an Arrhenius acid. So we ask you a question: define an acid according to Lewis theory, or define an acid according to Arrhenius concept. So any substance that increases the concentration of hydrogen ions or protons can qualify to be referred to as an acid. If you look at hydrochloric acid, when it dissociates in water, it forms hydrogen ions. So you have hydrogen ions that would result from there. Of course, there would be chloride ions also forming. So the presence of these hydrogen ions would cause the hydrogen ions that are present in the reaction mixture to increase, and it qualifies therefore to be referred to as an Arrhenius base. So that is the dissociation equation for HCl. So the hydrogen ions would be present in solution in that particular form. But then notice that these species are forming in a solution that contains water molecules, and when you look at the structure of the water molecule, it has two hydrogen atoms bonded to one oxygen atom. This oxygen atom has got pairs of electrons that are not participating in bond formation. So these pairs of electrons can actually be used to interact with other compounds, such as in this case, we've got species that are positively charged present in the solution, and the oxygen atom in the water molecule is partially negative. So the two can interact to form what are referred to as hydronium ions, which actually is the form in which those species are going to exist whenever an acid is dissolved in solution. So the hydrogen ions interact with the water molecules from the hydrogen ions from the acid interact with the water molecules to form these species, which are hydronium ions. So those species are going to exist in this particular form. We can represent a dissociation equation simply the way it is, or we can represent it in this particular form, in which case we are going to have to consider the water molecules. So when you've got your acid there and you've got your base there, okay, so you've got your acid and you've got your base, then the hydronium ion, of course, I will introduce you to the concept of conjugate acid base pairs. So this is your acid, that is your base, this is your conjugate acid, and that is your conjugate base. So as we get to that part, I will define what a conjugate acid is and what a conjugate base is. Okay. An Arrhenius base is defined as any species that increases the concentration of hydroxide ions in aqueous solution. So you recall that there was a definition that we gave you for acids. Okay, we talked about, we said an acid is a substance which, when dissolved in solution, will produce hydrogen ions as the only positively charged species in solution, and a base is a substance which, when dissolved in solution, produces hydroxyl ions as the only negative charged species in solution. So you've got some similarities of some sort, but at this level, when we ask you to define a base according to the Arrhenius concept, you are going to give us not any other definition other than the one that you are seeing here. An Arrhenius base is defined as any substance that increases the concentration of hydroxyl ions. That is all. No more and no less. Okay. So common Arrhenius spaces will include the group 1 atoms of elements and group 2 hydroxides. That is, when group 1 atom metals or group 2 metals react or burn in oxygen, they produce oxides that are basic in nature. And when these oxides are dissolved in solution, they form alkaline solutions, which are referred to as alkalis. So an example of an alkali is sodium hydroxide, which is actually formed through combustion of sodium. It burns in oxygen to form sodium oxide, which is in water. It dissolves and forms sodium hydroxide, which is an alkali, a base. So when this base interacts with water molecules yet again, it is going to result in formation of those species. Okay, so the result of those in solution would lead to an increase in the concentration of hydroxide ions in solution, which makes this one to qualify to be categorized as an Arrhenius space. Okay, the limitation of the Arrhenius definition was this, that he focused so much on only the species that would form in solution. Okay, he forgot the fact that similar reactions can also occur in non-gaseous solvents, that is, in non-gaseous aqueous solvents, and as well as between molecules in gas phases. So the definition was restricted to only systems that were in aqueous solutions. So there was therefore a need to modify the definition of an acid and a base slightly away from the way, although of course incorporating ideas that we have looked at before, using the Lewis theory, the Arrhenius concept also. A third concept was brought about, which was based on what two different scientists had come up with. These were Bronsted and Lowry. There were two scientists by those names who refined the definition for acids and bases. And this one is quite useful in a broader range of chemical reactions. So it is going to encompass a lot of systems other than only those that are in aqueous form. So when we ask you to define an acid using the Bronsted-Lowry definition or concept or theory, if you like, you would have to define an acid as a substance which can behave as a proton donor. So you recall you probably were introduced to this particular definition when you're in secondary school, where you are told an acid could simply just be defined as a proton donor. So any substance which can act as a proton donor, as far as Bronsted and Lowry were concerned, qualified to be called an acid. And we know that a proton can be represented by a positively charged hydrogen ion. This is something that we are familiar with. So any substance which contains hydrogen bonded to a more electronegative element can thus behave as an acid. An example is, you know that chlorine is more electronegative when it interacts with hydrogen. Hydrogen will assume a partial positive charge. This one assumes a partial negative charge. So any electronegative element that to which hydrogen can be bonded would result in formation of what can be classified as an acid. And when dissolved in solution, you actually have hydrogen ions and chloride ions forming. The sulfate radical can interact with hydrogen to form sulfuric acid, which when dissolved in solution, initially you're going to have formation of hydrogen ions and hydrogen sulfate ions. You have acetic acid. Acetic acid is a combination of hydrogen and the acetate ion. So that qualifies to be called an acid also. A base, according to Bronsted and Lowry, is a substance which can behave as a proton acceptor. So any substance that accepts a proton qualifies to be classified or categorized as a base as far as this particular definition is concerned. So what you carry is not only one definition of what an acid is supposed to be or what a base is supposed to be. You would have to define a base depending on what the question requires you to do. We may put a restriction. We tell you define an acid using the Bronsted or redefinition, or define a base using the Arrhenius concept, or define an acid and a base using the Lewis concept. So you should be able to remember those definitions that we looked at previously, as well as these ones, this particular one that we have for the base. Any species which has a lone pair of electrons can thus behave as a base. So a very good example of a base that you can give is ammonia. Ammonia has got a lone pair of electrons, to which hydrogen, positively charged hydrogen ions, can bond. So when the hydrogen ions bond to the to nitrogen through those lone pairs, you're going to have the ammonium ion forming. So that's your base there. That is your acid, as it were, and what you have resulting is a conjugate acid. So hydroxyl ion qualifies to be called a base because it can interact with the hydrogen ions to form a molecule of water. You've got the carbonate radicals can interact with the hydrogen ions to form hydrogen carbonate radical. What I alluded to earlier, the aspect of conjugate acid-base pairs. I'm not sure if you did look at this at any particular point in time when you are doing your chemistry, but I'm sure if you had someone who was very good teaching you chemistry, they probably might have mentioned this. They told you that a conjugate acid is a substance which forms when a base abstracts a proton. So to abstract is to get or to obtain or to acquire. When a base acquires a proton, the resulting species is going to be referred to as a conjugate acid. Then when the acid loses or donates a proton, what remains of it is referred to as a conjugate base. That is, those are the simple definitions that I can give you for conjugate acids and conjugate bases. So you will have creation of these pairs where you've got conjugate acid pairs. So we would give you one pair, and one of the two things that are supposed to be in a pair, and they will tell you this is the acid, what is its conjugate acid supposed to, this is a conjugate base, what is its base supposed to be, or this is a conjugate acid, what is its conjugate, something like that. So the species formed when a base accepts a proton, the species that is going to form when a base accepts a proton can give up a proton and behave as an acid, okay, in the process. So you have this particular species accepting a proton to form this species which can behave as an acid. You have the hydrogen sulfate ion accepting a proton, forming this species, and this species can behave as an acid. You have the acetate ion interacting with a hydrogen ion, a proton, forming this particular species. So this can act as an acid. And you have the ammonium ion. Again, the ammonium ion interacts in somehow in a way where it changes into, so this is your acid here, then it can actually, the equation is actually reversed. So it accepts a proton here, then you have this which actually is supposed to behave as your acid there. Then water molecules also, this is just actually just the reverse of is it what we had in the previous slide, that is. So where hydroxide ions are interacting with protons to form this particular compound, which is water, which can act as an acid, as we are going to see along the way, where water molecules sometimes can be treated as acids or even as bases. Okay. These species in this way are known as conjugate acid base pairs, which I defined a conjugate acid and I defined a conjugate base. So when you look at this particular pair, for instance, the chloride ions, the chloride ion is a conjugate base of HCl, because this one can accept a proton to form this, which is a gas. Then the gas, which is an acid rather, the base, I mean the acid which is hydrogen chloride is the conjugate base of the conjugate acid of the chloride ion. So you are going to have these pairs. Another example that you might cite is where you look at ammonia. Ammonia is the conjugate base of ammonium ion, and the ammonium ion is the conjugate acid of ammonia. So you should make sure that you're familiar with this particular concept of deciding what a conjugate acid or a conjugate base of a given species is supposed to be. Okay. Okay. Yeah. So this slide. Okay, just a minute. Okay. Yeah. So we have those concepts. And let's put up my pointer here. Yeah. So acid strength. We have acids that we refer to as strong acids. A strong acid, which you recall the definition that we had given you, a strong acid is an acid that undergoes complete dissociation in solution. And strong acids, when you show their ionization equations or dissociation equations, they are represented by an arrow that will point only in one direction, meaning that the equilibrium is actually just concentrated on one side. When you look at the ionization equilibrium for strong acids, you will notice that it's going to lie very far much more to the right than it does to the left. If anything, when it comes to ionization equations for strong acids, at a given point in time, the number of molecules that you have for the acid that were present in the reaction mixture may reduce to zero because they are decomposing to form your products, which are the ions. So that is why we represent ionization equations for strong acids with an arrow that points only in one direction, because once all the species that you started off with, which are the molecules of your acid, will have undergone ionization, they are not going to be there in the reaction mixture. All that you're going to end up with would be the ions that would have come from the acid that would have undergone ionization. So that is why the statement here we have says ionization equilibrium lies far to the right. So this is not a concept that I have to re-explain to you guys. You are experts now. You did your chemical equilibrium topic effectively, and you know what this really means. So we are going to have more activities on the right hand side than we do have on the left hand side, such that at a later stage we will not have any molecules that were introduced into this particular system where there is ionization taking place. When you have a strong acid, you will have a very weak conjugate base resulting when your strong acid will have undergone ionization. For weak acids, you recall we defined weak acids as acids that undergo partial dissociation in solution. So the ionization is not represented fully, and for weak acids, we said you would have to use the single-headed arrows, okay, the partial arrows, one pointing in one direction and the other one pointing in the other direction, which indicates that there's going to be establishment of some chemical equilibrium of some sort. So when you look at the ionization equilibrium for weak acids, it's going to lie very much far to the left. So what does that mean? It means, as you all do know, that at a given point in time, you're going to find more molecules of the acid in the reaction mixture than you're going to find the ions that will have come from the acid itself, which is undergoing ionization. So we're going to have more molecules of the acid than the ions that are resulting from the ionization process. So it lies far much more to the left of the reaction system itself. And when you've got a weaker acid, the conjugate base is going to be a stronger one. So the weaker the base, the stronger its conjugate base. Water is a very useful substance which can behave sometimes as an acid and sometimes as a base, depending on what it is interacting with. We classify water as we were told previously that if you needed a solution that was neutral, you would have to use water because water is neither acidic nor basic. But here we are using water to act as an acid or as a base, and you're going to see how this is going to be justified. So at a given temperature, water, which is referred to as an amphoteric substance because it can have properties of acids and bases, at a specific temperature of 25 degrees Celsius, which is referred to as room temperature, water undergoes auto-ionization. Okay, so this is an auto-ionization equation for the water molecule to form hydrogen ions and hydroxyl ions. Then you see that we have another constant that has been introduced, which is the Kw constant. This constant is for the auto-ionization of water. So equilibrium constant for the auto-ionization of water, that is represented by this equation that you see here. So if you knew the concentration of hydrogen ions and the concentration of hydroxyl ions, and you multiplied the two, you would get a constant. Provided the temperature is kept at that 25 degrees Celsius, the constant that you're going to get is going to be 1.0 times 10 to the power negative 14. Okay, that is for auto-ionization of water at 25 degrees Celsius. If you increase the temperature, the system is going to need a supply of heat energy. It's going to absorb most of the heat energy that you're going to feed into the system, in which case the dissociation is going to become endothermic. And the ionic product of water is going to be slightly higher at a higher temperature. So if when you're carrying out studies where you are comparing the ionization of, say, a given substance with another, if you do not want any influence, or if you want influence from water molecules, that the influence that should be known, because you know how water behaves at a given temperature, you would need to keep the temperature constant. So when the temperature is kept constant, you may ignore the effect that would come from the water, from the auto-ionization of water, because you have kept the temperature constant. But when you change the temperature, it becomes very difficult for you to actually get results that might be regarded to be reliable at the end of the day, because you keep changing the temperature at which the reaction is taking place. So make sure that the temperature is maintained at 25 degrees Celsius, where the Kw value is actually known. There are three possible situations that you are going to notice when you study this behavior of water further. You notice that when the water is pure, the hydroxyl ion concentration and the hydronium ion concentration. So you've got, this is the hydronium ion and that is the hydroxyl ion concentrations. These two concentrations are equal when the water is pure. Such that therefore, if you multiply the concentration of hydroxyl ions, hydronium ions and hydroxyl ions, the two, because they are equal, this can simply be gotten by just squaring the concentration for the hydronium ions. Then you're going to get the Kw value, which is the equilibrium constant for the auto-ionization of water. If you were to let the concentration of hydronium ions be equal to the concentration of hydroxyl ions, which is actually supposed to be the case for pure water, and that being equal to X, then you can substitute. Where there is the square of the hydronium ion, the concentration here, you put X there, then you square this, you're going to have that. So X, therefore, you will be found by taking the square root on both sides, which will give you 1.0 times 10 to the power negative 7. So these are values that you have to master, because you would have to use them at some point. You're going to see when we start looking at calculations, there are questions that would involve doing some calculations. And if you're able to remember these constants, okay, you will be able to actually answer questions without any difficulties. If the concentrations of hydrogen ions and the concentration of hydroxyl ions are equal, then the solution would be said to be a neutral one. But should the concentration of hydrogen ions increase, then the solution is going to be said to be acidic. Should it reduce, the solution will be referred to be as a basic, or regarded to be a basic solution. Okay. Strength of acids. We did allude to this. We know that strong acids would undergo complete dissociation, and you're going to have formation of the hydronium ion and the conjugate base. For strong acids, their ionization equations are represented using an arrow that points only in a single direction, because at some point those are there in solution. For instance, when you're looking at these strong acids, hydrochloric acid, nitric acid, and sulfuric acid, if you were to look at the ionization equation for hydrochloric acid, you will notice that you're going to have hydrogen ions and chloride ions forming in solution. So at a later stage, those are not going to be there in solution. In your reaction mixture, they would have been converted into those two. That's what it means for a complete dissociation. So if you knew the concentration of your HCl, for instance, it's going to be very easy for you to actually find the concentration of the species that are resulting from this dissociation reaction, because we know that those are not going to be there at some point, so they would have, all of them, the concentration that we had, this one would have been converted into the concentrations for those two. A very simple example that you can cite is that of HCl itself interacting with water molecules to form the hydronium ions. So the hydronium ions can also be represented by just the hydrogen ions. So because we know that the hydrogen ions are interacting with water molecules, the water molecules which have got lone pairs of electrons on the oxygen atom to form those species. So we can represent a dissociation equation using this expression here, or if we choose to include water molecules, then we're going to have the hydrogen ions coming from the acid interacting with the water molecules to form the hydronium ions. So if you knew the concentration of the acid, then it's going to be very easy for you to establish what the concentration of the hydrogen ions or the hydronium ions is going to be, because the dissociation equation is a one-to-one kind of expression, which you simply determine the concentration. You determine the concentration of the resulting species using the of what is the acid. So in this case, the concentration of the hydronium ions will be equal to the concentration of the acid which you would have started off with. Okay. For weak acids undergo partial dissociation in solution, and the dissociation equation will be represented using single headed arrows which will point in either directions. And at equilibrium, the dissociation equation is going to be represented by that, where you have your acid and the water molecule acting as a base, interacting to form the hydronium ion, which is regarded as your conjugate acid, and you have this that would have remained from the acid, regarded as the conjugate base. So a weak acid is one which is worse proton donor than the hydronium ion. Examples of weak acids, you recall that we had told you that almost all organic acids are classified as weak acids. All organic acids are classified as weak acids. You've got methanoic acid, you have ethanoic acid, which is also commonly known as acetic acid, propanoic acid, pentanoic acid, hexanoic acid. All those are weak acids. Then you've got some salts that will have some acidic properties. So sodium hydrogen sulfate is a salt, yet it has got some acidic properties. You have oxides also that might have acidic properties, but they are weak acids. Carbon dioxide, for instance, is an acidic oxide. It acts as an acid, and it's a weak acid as it were a weak uh, acidic oxide. We are familiar with the concept of equilibrium expressions. So we have introduced ourselves to one more equilibrium constant, which was the Kw, which is the equilibrium constant for autoionization of water. So I would like us to look at another constant in relation to these equilibrium expressions. So the equilibrium expression for the dissociation of a weak acid is given as follows. The equation for the dissociation of a weak acid is going to be given by that. Make sure that you use that arrow to show that at equilibrium, you are going to have the species that are undergoing dissociation still present in the reaction mixture, as well as the species that are resulting, such that at some point, there is going to be establishment of some chemical equilibrium of some sort where the rate at which that is decomposing to form those is going to be equal to the rate at which the two of them are interacting together to form what you'll have started off with. So the expression that is going to be given in terms of this ionization equation is referred to as the Ka, which is the equilibrium expression for the dissociation of an acid. So this is the dissociation constant for an acid, which is the Ka. Okay, the dissociation constant for an acid given in terms of what we have as the law of mass action. Everything is the equilibrium expression for the dissociation reaction of a weak acid. So if you knew the concentration of the acid, then you would be able to establish what the concentration of the resulting species would be. But of course, when writing the expression, recall how I told you that the expression can be written in this manner, or you can include water molecules. But when you include water molecules, when it comes to writing the equilibrium expression itself, the water molecules will not participate in the equilibrium expression. You are going to simply focus on the concentration of the acid and the concentration of the species that are resulting from the dissociation of this particular acid, such that the expression can either be given in this form or in this other form, depending on what you prefer as the appropriate way of representing your equilibrium expression. So like we said, K Ka is the acid association constant for weak acids. K is of weak acids is relatively small. The concentration of hydrogen ions can be calculated using this expression. You can find concentration of hydrogen ions or hydronium ions by simply multiplying the value that you will have been given for the equilibrium constant, Ka, and the concentration of the acid. Then you take the square root of the product. That is going to give you the concentration for the hydrogen ions or the hydronium ions that are present in solution. When it comes to bases, of course, we have those that are strong, which will have a similar definition to the definition that we gave for a strong acid. So strong bases undergo complete dissociation in solution. And examples of strong bases are potassium hydroxide, sodium hydroxide, and barium hydroxide. So these are going to dissociate also when they are dissolved in solution. What is the hand? Yes, please. Yes, go ahead. Hello? Yes, yes, Mike, yes. There's a hand from Mike. Mike? The internet is a little bit shaky. Hello? Mike, are you talking? Are we able to hear Mike? Hello? Mike, are you still there? Mike, are you still there?
I think, sir, there's a network problem here.
Can I continue?
Yes, sir, but could you kindly repeat
Hello? Mike?
the slide? Yes, sir.
Okay, it's like, can you guys hear me?
Challenges. A lot of people are heading to.
Okay, yes, Mike, you had the question?
Yes, could you kindly repeat the slide?
Oh, there's where did you lose me from? Which slide?
From slide 17. Most of the people don't get what you are saying. Starting from slide 17.
17. Okay. Okay, from 17. Let me go back slightly then. From 17. Okay, yeah, so on this particular slide here, what I was saying was that we are introducing another equilibrium constant in addition to the ones that we have looked at so far. The most recent one was the Kw, which is the equilibrium constant for auto-ionization of water, we said. For auto-ionization of water. So now we have another one, which is the Ka, which is the equilibrium constant for dissociation of a weak acid. So I said there are two ways in which we can write our dissociation equations for weak acids. We can write a dissociation equation in terms of the acid itself and the species that are resulting without focusing so much on the water in which the acid is dissolving, in which case our expression is going to be given in terms of K, which is the equilibrium constant for the dissociation of an acid, in relation to what we have on the other side, which is essentially everything is a law of mass action and is referred to as the equilibrium expression. Or you can write your dissociation equation where you also have to include the water molecules as participating in the dissociation reaction itself. But of course, the hydrogen ions that would come from the acid would go to the water molecules and they would form hydronium ions. So hydronium ions form. If you want to consider them as they are, then your expression is going to change slightly, where you put the concentration of the hydronium ion and the concentration of the conjugate base. But the water molecule itself is not going to participate in the law of mass action. You're going to leave it out. Okay, that is the way this is supposed to be written, because the significance that the water ionization will have no significance whatsoever in terms of what the constant is going to be in relation to its value. The contribution is very insignificant, so we don't consider the concentration of the water molecules due to auto-ionization. So we leave that one out. We are simply going to focus on the species that are resulting when the acid itself interacts with the water molecules and undergoes ionization. Okay, hope that was clear. Then I went on further to say the Ka, like I introduced it, is the equilibrium, is the ionization constant. It's the acid ionization constant for weak acids. If you have the K value given to you, which values are usually very small for weak acids, and the concentration of the acid is given, you can calculate the concentration of your hydrogen ions or the hydronium ions. So you can use those two alternate interchangeably. If you want, you can use the symbol for the proton, or you can use the symbol for the protonated water molecule that is called the hydronium ion to mean the concentration of hydrogen ions that are going to be present, the concentration that would be in the solution in which the acid is dissolved, coming from the acid itself, which is undergoing dissociation. So you simply multiply the Ka value and the value of the concentration for the acid, then you take the square root of the product. That would give you the concentration of the acid. That is when you are dealing with the weak acids, which usually have got Ka values that are very small. I hope it is clear now and everyone was able to get me. It's a challenge with our internet connectivity. We've got the poorest type of internet. I don't know what Zikta has been doing about this poor internet connectivity with our mobile providers. It's a problem. It's a problem everywhere. You will bear with us. But if you face challenges and you are not able to hear me, please let me know so that we repeat on some of the things that we probably might have talked about. Okay, good. Okay, so if we get a signal, it means people are able to hear. Good. Okay. Yeah. So the time is 16 hours. Let me just talk about one last thing, then we can find time again to meet through your representative. A representative will be able to communicate to me when you're going to have some free time until we learn the entire topic, you guys, all the way up to the very end. Like I said at the start of this session, your friends participated overwhelmingly in the morning. I had sessions from 12 to 13, 13 to 14, 14 to 15, and that's why I delayed to start our session, because I was attending to the last group from the other lecture group. So can we all attend? Encourage your friends to attend. Log in. Even if we're talking, who knows, I might bring in 1, 2, 3, 4 concepts that might pop up in your test or in your exam. And if you're not here when we're talking about them, you may not really be able to answer questions the way I might prefer. That question should be answered as your examiner. So please make sure that you attend these sessions every time we're having them. Yeah, so the last slide that I want to talk about is this one, where we have got bases. So strong bases undergo complete dissociation, and examples of strong bases are sodium hydroxide, potassium hydroxide, and barium hydroxide. So when these undergo dissociation in solution, you are going to have formation of hydroxyl ions. If the base that you have would result in formation of those species in a 1-to-1 ratio, then it becomes very easy for you to determine what the concentration of the hydroxyl ions is going to be. Okay, so you would have to, so with these ones, because the base is strong, you may not have to use, you are not encouraged to find the concentration of hydroxyl ions by multiplying the what is the Kb, in this case, the Kb constant, and the concentration of the base, then you find the square root. No. For strong bases, that is not encouraged. So how are you going to find the concentration of the hydroxyl ions? You will have to take note of the ratios in which these species are ionizing. In this case, for sodium hydroxide, this is a 1-to-1 ratio throughout. So the concentration of the hydroxyl ions would be equal to the concentration of the sodium ions and the concentration of the hydroxyl ions. For barium hydroxide, you have to take note that the 2 that is outside here would mean you're going to have a 2 in front of the hydroxyl ions when this undergoes ionization. So the concentration for barium that will have been given is supposed to be multiplied by 2 for you to get the concentration of the hydroxyl ions, and then you will use it to do calculations that might need to be done. When it comes to weak bases, we know that a weak base is one that undergoes partial dissociation in solution. So the way we are going to treat these, we would have to bring in the concept of the law of mass action, in which case we would use what is now referred to as Kb, which is the dissociation constant for a weak base. The base dissociation constant, as it were, or base ionization constant. So the any substance that can accept a positively charged proton qualifies to be called a base. In this case, this one interacts with the water molecules. It forms an ammonium ion, which is a conjugate acid, and then what remains from the base? In this case, this is your base. This is your acid. So your water is acting as your acid, as an acid there. Then when the base interacts with the water molecules, you have this, which is the conjugate acid, then the conjugate base. So the expression is going to be given in terms of the conjugate acid, the conjugate base, in terms of their concentrations, and the concentration of the base itself. So if the Kb is known and you're asked to find the concentration of hydroxide ions that are going to form in solution, you would have to multiply the value of Kb and the value of the concentration for the base, and what you're going to get is going to give you the concentration of the hydroxyl ions that are forming in this particular solution. So this is how you're going to have to treat weak bases. So take note that we have dealt with a number of constants. We started with the K, we went to the Kp, we went to the Sp, we have the Kw, we've got the Ka and the Kb. So all these should be used correctly. We should not mistaken one for another. Okay. Yeah. So we end our session here. We are going to continue next time. If you find free time again, work with your group representative so that he communicates to me. Then we look for a time when all of us can attend these learning sessions. They are not supposed to be for only a small group of people. Everyone is supposed to attend, because all of us will be subjected to the same material at the end of the day. So as you agree on what time we are supposed to meet, if you notice that you've got challenges, you've got other lectures that you need to attend to, negotiate with your group representative so that he and I can negotiate nicely on which specific time would be appropriate for everyone to be part of these learning sessions. Okay, so I'll see you next time, my good friends. Thank you so much for attending this particular session today. Next time.
Okay. So we are kind of asking for the same notes.
Notes, definitely they will be sent to you. Don't worry. The notes will be sent, will be shared through your representative.
Thank you.
All right. Sure. Okay.